Hello and welcome to the Sleepy Science Channel. Tonight, we gently drift toward one of the deepest and most fascinating mysteries ever discovered. It is something that surrounds you, moves through you, and outweighs everything you can see in the night sky. It does not shine, it does not glow. Yet without it, the universe we know would likely never have formed. Dark matter is the hidden architecture of the cosmos. It shapes galaxies, guides their motion, and binds enormous structures together across unimaginable distances. We cannot touch it or observe it directly, and yet its presence is written clearly in the motion of stars and in the bending of light itself. Whenever a galaxy spins faster than it should, or a massive cluster holds together against all expectations, this invisible influence quietly reveals itself. In this journey, we will wander through ideas that stretch from the earliest moments after the universe began, all the way to modern experiments hidden deep underground. It is a story filled with unanswered questions, careful observation, and a growing realization that reality may be far richer than it first appears. If you enjoy these calm explorations, feel free to like the video, subscribe to the channel, or leave a thought below. It helps other curious minds find their way here as well, one sleepy traveler at a time. But for now, allow your breathing to slow. Let the weight of the day gently dissolve. Let your body relax while your mind settles into this vast and fascinating mystery. And so, we begin. Dark matter outweighs visible matter and shapes every galaxy you see. If you could somehow place the entire universe on a giant scale, most of the weight would come from something that gives off no light at all. The stars, planets, glowing nebulae, clouds of gas, and every luminous object in space would together make up only a small fraction of the total mass. The larger portion belongs to an invisible component that surrounds and permeates everything. This hidden majority behaves like a deep gravitational landscape into which ordinary matter slowly settles. Where that landscape becomes slightly denser, gas begins to gather. The gas cools, collapses, and eventually forms stars. Where the invisible structure is thinner, galaxies struggle to grow. In this way, the night sky is not simply a collection of bright objects scattered randomly across space. It is also a map of an unseen framework that quietly determines where galaxies appear, how large they become, and how they assemble into families across the vastness of the universe. Galaxies spin so quickly that starlight alone cannot hold them together. Imagine a spinning merry-go-round. As you move outward from the center, the outer horses must travel faster and faster to keep up with the rotation. Astronomers once expected galaxies to behave in a similar way if their mass came mostly from what we can see. But observations revealed something very different. Instead of slowing down with distance from the center, many galaxies continue rotating at nearly the same speed far beyond their bright cores. This creates a puzzle, because the outer stars should eventually be flung away into space. Yet they remain bound. The only explanation is that there must be additional gravity holding the galaxy together. Gravity produced by a vast amount of unseen mass. One famous example is the Andromeda Galaxy. Stars far beyond its bright disk still move at surprisingly high speeds. Something massive extends far beyond the visible glow, wrapping the galaxy in a huge invisible halo. This mismatch between expected motion and observed motion became one of the clearest clues pointing toward unseen matter. Most of the Milky Way's mass exists in a vast invisible cloud. If you could travel far above our galaxy and look back, you would see the familiar spiral disk glowing softly with billions of stars. But what you would not see is the much larger region of mass surrounding it on every side. This invisible component stretches far beyond the disk and far beyond most of the star fields we can observe. It holds the galaxy together like a deep gravitational basin. Astronomers infer its existence by tracking the motions of distant halo stars, globular clusters, and small companion galaxies orbiting far from the center. These objects behave as if enormous amounts of mass are spread throughout the outskirts, even though very little light is present there. This matters even for us. Our solar system moves through this extended environment as it orbits the Milky Way. And when the Milky Way eventually collides with the Andromeda Galaxy billions of years from now, the invisible halos of both galaxies will begin interacting long before their stars ever meet. Without dark matter, the early universe would not have formed galaxies so quickly. In the young universe, ordinary matter was hot and restless. Radiation pushed it around, preventing it from gathering easily into dense regions. Dark matter behaves differently. Because it does not interact with radiation in the same way, it could begin collecting into dense regions much earlier. These early clumps acted as gravitational seeds. As the universe cooled, gas began falling into those seeds. Once enough gas accumulated, the first stars ignited, and galaxies slowly took shape. This process helps explain why we observe galaxies already present when the universe was still very young. It also explains how those early galaxies could grow into larger systems through mergers and gradual accretion. In a sense, dark matter gave the universe a head start in building cosmic structure. Without it, galaxies would likely have appeared much later, and the universe might look far emptier than it does today. The largest cosmic structures resemble a vast web supported by dark matter scaffolding. On the largest scales, the universe is not evenly filled with galaxies. Instead, galaxies gather into filaments, sheets, and dense knots separated by enormous empty regions known as voids. This pattern is called the cosmic web. Computer simulations that include dark matter naturally reproduce this structure. Tiny ripples in the early universe grow over billions of years into long strands of matter connecting dense clusters of galaxies. Ordinary gas flows along these invisible gravitational channels. As it collects and cools, stars form and illuminate the structure. Over time, the web becomes a kind of cosmic geography that guides where matter travels and where galaxies flourish. Modern sky surveys map this structure by measuring the positions of millions of galaxies across vast regions of space. The astonishing result is that the cosmic web is not just a poetic metaphor. It is a measurable structure, strong evidence that an unseen framework has shaped the universe since its earliest moments. The idea of dark matter first emerged from a problem involving missing mass in galaxy clusters. When astronomers began studying clusters of galaxies as single systems, they expected the visible galaxies to account for the cluster's gravity. But measurements told a different story. Galaxies inside clusters were moving far too quickly. If the cluster contained only the matter that telescopes could see, it should have flown apart long ago. Instead, the clusters remained bound. Something heavy had to be present, something invisible. Galaxy clusters became ideal laboratories for this mystery. They are enormous structures that have existed for billions of years, allowing gravity to reveal its true influence. The missing mass problem was not a small error in calculation. It was a persistent mismatch between motion and visible matter. And it hinted that the universe contains a deep and hidden component. Almost a century ago, the astronomer Fritz Zwicky argued that galaxy clusters must contain large amounts of unseen matter. In the early years of extragalactic astronomy, Zwicky studied the Coma cluster, a massive gathering of galaxies. He treated the cluster like a swarm of bees orbiting a shared gravitational center. By measuring how fast the galaxies moved, he could estimate how much mass the cluster must contain in order to keep everything bound together. The result was startling. The cluster required far more mass than the combined light of its galaxies could possibly represent. Zwicky proposed that a large portion of the cluster's mass was invisible. He called this missing component dark matter. At the time, the idea was bold and controversial. The universe itself had only recently been recognized as vast and filled with distant galaxies. Many astronomers were reluctant to accept the existence of an entirely new type of matter based only on indirect evidence. Yet the logic was simple. Gravity leaves traces in motion, and the motions Zwicky observed suggested that the cluster was far heavier than visible starlight alone could explain. It was an early warning that the cosmos might be hiding something immense. Decades later, the work of Vera Rubin made the mystery impossible to ignore. Rubin and her collaborators carefully measured how fast stars and gas clouds move at different distances from the centers of spiral galaxies. Instead of relying on a single galaxy cluster, they examined many individual galaxies across the sky. Their results were remarkably consistent. The outer regions of spiral galaxies were rotating far too quickly for the visible matter to hold them together. Again and again, the same pattern appeared. The effect was not rare or unusual. It seemed to be a basic rule of galactic structure. The implication was clear. Galaxies must be surrounded by enormous halos of unseen mass. Rubin's measurements transformed dark matter from an obscure theoretical idea into one of the central mysteries of modern astronomy. This was no longer an isolated anomaly. It was a widespread feature of the universe, repeated across countless galaxies. Computer simulations, including dark matter, recreate the large-scale structure of the universe. When cosmologists want to test ideas about how the universe evolved, they often create simulated universes inside powerful supercomputers. These simulations begin with the tiny density ripples observed in the cosmic microwave background, the faint afterglow of the Big Bang. Then gravity is allowed to run forward through billions of years of cosmic time. When dark matter is included in these simulations, something remarkable happens. The virtual universe begins forming structures that closely resemble the real one. Long filaments emerge. Dense galaxy clusters appear at the intersections of those filaments. Vast empty voids open between them. The resulting pattern looks strikingly similar to the cosmic web mapped by telescopes. Even more intriguing is the fact that the simulation does not need to know what a galaxy looks like. It only requires the laws of gravity and the correct amount of unseen mass. From those simple ingredients, large-scale structure naturally emerges. Moments like this are rare in science. A mysterious ingredient suddenly makes the entire recipe work. Without dark matter, these simulations struggle to reproduce the observed universe. If the same cosmic evolution is simulated using only ordinary matter, the results look very different. Ordinary matter interacts with radiation. It heats up, cools down, and experiences pressure. In the early universe, it was tightly coupled to intense radiation fields. These effects make it much harder for matter to collapse quickly into structures. As a result, galaxies in these simulations form too late. The pattern of clustering also fails to match what we observe across the sky. The simulated universe appears smoother than the real one. It is almost as if one is trying to build mountains in a world where the crust never quite buckles or folds. This mismatch appears in several ways. Galaxies cluster too weakly. Large structures form too slowly. Intermediate scales contain too little structure. Dark matter solves all of these problems at once. It not only explains why galaxies spin too quickly, it also helps reproduce the overall population of galaxies, clusters, and cosmic filaments observed throughout the universe. We cannot see dark matter directly, but we can weigh it through gravity. Light is not required to measure mass. Motion is enough. Astronomers observe how stars orbit inside galaxies, how galaxies move within groups, and how extremely hot gas behaves inside massive galaxy clusters. From these motions, they can calculate the strength of the gravitational field required to produce them. Then they compare that required gravity to the mass of all visible matter, stars, gas, and dust that telescopes can detect. Again and again, the visible matter falls short. It is like hearing many footsteps echoing in a dark hallway and realizing there must be far more people present than the few silhouettes you can see. This is why the mystery of dark matter is so compelling. The evidence does not rely on a single observation or one type of instrument. Instead, it arises from many independent cosmic motions that all point toward the same conclusion. Galaxies live inside enormous halos of dark matter. A galaxy is not simply its shining disk or glowing bulge. Surrounding it is a much larger halo of invisible mass extending far beyond the outermost visible stars. This halo acts like a gravitational home. It helps galaxies form and remain stable. It also explains why many smaller galaxies orbit larger ones, like satellites. These satellites travel through the outer halo, like boats drifting along invisible currents. The halo influences the entire history of a galaxy. When galaxies pass near each other, their halos can overlap and interact. These interactions can alter orbital paths and trigger slow mergers that reshape both systems. Over billions of years, halos also accumulate smaller clumps of matter. Some become satellite galaxies. Others are torn apart into streams of stars. In this picture, the visible stars are almost like decorations. The halo is the true structure that defines the galaxy. Colliding galaxy clusters reveal dark matter through the separation of mass and gas. Galaxy clusters are the largest gravitationally bound structures in the universe. When two clusters collide, the event becomes a natural experiment on a cosmic scale. The hot gas within each cluster crashes together and slows down because gas interacts through pressure and collisions. The galaxies themselves mostly pass through the collision unaffected. The distances between stars are so enormous that direct collisions are extremely rare. But something even stranger happens. Gravitational lensing maps, which reveal the distribution of total mass, show that most of the mass follows the galaxies rather than the gas. One famous example is the bullet cluster. In this system, two clusters have passed through each other. X-ray images show hot gas slowed and concentrated between them. Yet the majority of the gravitational mass lies ahead of the gas, following the galaxies. It is as if most of the weight of the system slipped through the collision, while the visible material became trapped. This observation strongly suggests that the dominant mass component does not behave like ordinary matter. Instead, it behaves like something that barely interacts, even during one of the most violent events in the universe. Dark matter can also reveal itself through the bending of light. Gravity does not only affect motion, it also curves the fabric of space itself. When a massive object lies between us and a distant galaxy, it can act as a natural gravitational lens. Light from the background galaxy bends around the mass and travels toward us along curved paths. Sometimes the background galaxy appears stretched into arcs. Sometimes it forms a nearly perfect ring. In other cases, multiple images of the same galaxy appear. What makes this technique so powerful is that gravitational lensing depends on total mass, not on brightness. This means astronomers can map invisible matter simply by measuring how it distorts the shapes of distant galaxies. In some cases, strong lensing reveals large concentrations of mass where very few stars are present. It also allows astronomers to observe extremely distant galaxies that would otherwise be too faint because the gravitational lens magnifies their light. In this way, the unseen component of the universe does not only shape what we observe, it also helps us see farther than we otherwise could. Even now, streams of dark matter may be passing through Earth. Our planet moves through the Milky Way, and the Milky Way itself moves through its own vast halo of dark matter. If dark matter consists of particles, then Earth is constantly drifting through a faint, invisible wind of them. Most of these particles would pass through rock, oceans, and even our bodies without leaving any trace. That is why scientists build detectors deep underground. Thick layers of rock shield these experiments from cosmic radiation and other sources of noise. Inside these quiet laboratories, extremely sensitive detectors wait for a rare moment when a passing particle might nudge an atomic nucleus or an electron. The difficulty is that almost everything else in the environment can mimic such tiny signals, from natural radioactivity to microscopic contamination. So these experiments are designed like silent listening rooms for the universe. Even a single convincing signal could reveal a new form of matter that has been passing through us all along. Spiral galaxies rotate with surprisingly flat speed profiles far from their centers. If gravity came mainly from the bright stars concentrated near galaxy's center, you would expect orbital speeds to decrease as you move farther outward. This is exactly how planets behave around the Sun. The farther a planet is from the Sun, the slower its orbital speed becomes. But galaxies do not follow that pattern. Instead, many spiral galaxies continue rotating at nearly the same speed, even far beyond the region where most of their visible light is located. This phenomenon is known as a flat rotation curve. It is as if a carousel maintained the same speed at the outer edge even when almost no visible material remained to provide the inward pull. The implication is striking. Mass must be spread out in a broad, faint envelope that extends well beyond the visible disk. That unseen mass influences how galaxies behave when they encounter one another. It affects how strongly they pull on neighboring galaxies, how their disks remain stable, and how they maintain their shape over billions of years. A simple graph of orbital speed versus distance becomes a doorway into an invisible component of the universe. Galaxy clusters also contain enormous reservoirs of hot gas that would escape without additional gravity. In a massive cluster, the space between galaxies is filled with extremely hot gas glowing in X-rays. This gas can reach temperatures of tens of millions of degrees. At such high temperatures, the gas naturally wants to expand and drift outward into space. Yet clusters manage to hold this gas in place for billions of years. The only force capable of confining it is gravity. When astronomers calculate how much gravity is required to trap that hot gas, they find that the visible galaxies do not supply nearly enough mass. The gas itself contributes significant mass. In some clusters, even more than the stars. But the total still falls short. This shortfall is particularly important because the gas is not invisible. X-ray telescopes can measure its temperature and distribution very precisely. From those measurements, scientists can determine the pressure pushing the gas outward. The fact that the gas remains confined tells us something profound. The cluster must be surrounded by additional mass that cannot be seen. Gravitational lensing can map mass even when no starlight exists. Sometimes the universe provides a map without using light as ink. When a foreground galaxy or cluster lies between us and a more distant region of space, its gravity bends the incoming light from background galaxies. Those distant galaxies appear distorted, stretched, shifted, or curved into arcs. By measuring those distortions carefully, Astronomers can reconstruct the distribution of mass responsible for the lensing effect. Remarkably, this method works even when the mass itself produces little or no light. In some cases, the strongest lensing signal comes from regions where very few stars or glowing gas clouds are present. This tells us that the mass is real even when the light is missing. Gravitational lensing also allows astronomers to observe galaxies that would otherwise be too faint to detect. The lensing mass acts like a natural telescope, magnifying distant objects. In this way, invisible matter not only shapes the universe, it sometimes helps reveal it. Weak gravitational lensing reveals subtle alignments across millions of galaxies. Not all gravitational lensing produces dramatic arcs or rings. In most cases, the effect is incredibly subtle. A single distant galaxy might be stretched by only a tiny amount, far too small to trust on its own. But when astronomers measure the shapes of millions of galaxies across a large region of sky, patterns begin to appear. Those tiny distortions align with each other. They trace the distribution of mass between us and the distant galaxies. This phenomenon is known as weak gravitational lensing, and it has become one of the most powerful methods for mapping invisible matter. It works somewhat like reading wind direction from a field of grass. A single blade does not reveal much, but when an entire meadow bends in the same direction, the wind becomes clear. With careful statistical analysis and precise control of telescope distortions, weak lensing maps can reveal cosmic filaments, dense clusters, and enormous empty regions, even when those structures contain little visible light. In effect, the entire sky becomes a detector. Distant galaxies form the grid used to measure the universe's invisible architecture. Strong gravitational lensing can produce spectacular Einstein rings. Under the right conditions, gravity becomes an extraordinary cosmic sculptor. If a massive object lies almost perfectly aligned between us and a distant galaxy, the bending of light can become symmetrical. The light from the background galaxy wraps around the lensing object, forming a luminous circle. This phenomenon is called an Einstein ring. It is not merely an optical illusion. It is the same galaxy appearing along many different light paths through curved spacetime. The size and thickness of the ring depend on the mass of the lensing object and how that mass is distributed. This allows astronomers to measure the mass of the lens with remarkable precision, including the portion that produces no light. Strong lensing can also split a distant galaxy into multiple images. Because the light travels along different paths, those images may even appear at slightly different times if the source varies in brightness. Each image becomes a clue. Together, they reveal the hidden structure of the lensing mass. In these situations, gravity literally turns space itself into a measurable lens. The cosmic microwave background carries the early gravitational imprint of dark matter. Long before the first stars existed, the universe was filled with a hot, dense plasma of particles and light. Photons scattered constantly off charged particles, preventing light from traveling freely. Eventually, the universe cooled enough for atoms to form. At that moment, light was finally able to move freely through space. We still observe that ancient light today as the cosmic microwave background. It appears as a faint glow coming from every direction in the sky. At first glance, the microwave background looks almost perfectly uniform. But careful measurements reveal tiny temperature variations. These fluctuations are incredibly small, yet they carry enormous information. They reflect slight differences in density that existed when the universe was only about 380,000 years old. Those small variations eventually grew into galaxies, clusters, and cosmic filaments. Dark matter plays a crucial role in shaping these patterns. Because dark matter does not interact with radiation, it could begin forming gravitational structures earlier than ordinary matter. Its presence alters how density waves grew and evolved in the early universe. As a result, dark matter leaves a distinctive signature in the microwave background. By measuring this signature with extraordinary precision, scientists can estimate how much invisible matter exists in the cosmos, even though the microwave background itself is made of light. Tiny temperature ripples hint at the invisible mass shaping the first structures. Those faint ripples in the microwave sky form a kind of cosmic blueprint. They show where matter was slightly denser and where gravity pulled just a bit harder. Over time, these small differences grew larger. Dense regions gradually attracted more material, while emptier regions became vast cosmic voids. Dark matter helps explain how this growth could begin so early and proceed so efficiently. The ripples represent conditions at the moment when the universe became transparent. From that starting point, scientists can run computer simulations forward through cosmic history and compare the results with the galaxies we observe today. When the simulations include dark matter, the predicted universe looks strikingly similar to the real one. It is astonishing that a faint afterglow from the young universe can tell us about a form of matter we still cannot capture directly. The earliest light becomes evidence for unseen weight. Dark matter clumped earlier than ordinary matter. In the universe's earliest chapters, ordinary matter was not free to gather wherever gravity pulled. It was tightly mixed with radiation in a hot plasma. Radiation pushed back whenever matter attempted to collapse. It was somewhat like trying to form droplets of fog while strong winds constantly stirred the air. Dark matter was different. Because it does not interact with light in the same way, it could collapse into denser regions earlier. These regions formed a network of gravitational wells long before atoms existed. Later, when the universe cooled and ordinary matter became neutral, gas could finally fall into those wells. This sequence is crucial. It means that dark matter set the early rhythm of structure formation, while ordinary matter joined the process later once conditions allowed it. That timing explains why galaxies could appear when the universe was still relatively young. This early clumping created the seeds for the very first star-forming regions. The first stars did not ignite in completely empty space. They required places where gas could gather, cool, and compress until gravity took full control. Early halos of unseen mass provided exactly those gathering points. Gas flowed inward toward these invisible wells. As it fell, it heated up. Over time, however, it began losing that heat through simple molecules. One of the most important of these was molecular hydrogen, which could radiate energy away even in an environment where heavier elements were almost absent. As the gas cooled, it sank deeper into the halo's gravitational pull, becoming denser and denser. Eventually, the gas fragmented into the first clouds capable of forming stars. Those earliest stars were probably very different from most stars that exist today. The early universe contained almost no carbon, oxygen, or dust, elements that normally help gas cool efficiently. Without them, star formation required a delicate balance between gravity and primitive chemistry. In this way, dark matter helped prepare the stage for the first starlight to appear in the universe. Dark matter does not appear to emit or absorb light. One of the simplest and strangest clues about dark matter is this. If the missing mass interacted with light the way ordinary matter does, we would be able to see it. Heated matter glows. Dust blocks and scatters radiation. Gas absorbs specific wavelengths of light. Even extremely faint stars still emit some detectable glow. But dark matter behaves differently. It appears to be almost perfectly transparent to electromagnetic radiation. It neither shines nor casts shadows. Because of this, astronomers must observe it in indirect ways. They look not for its brightness, but for its gravitational pull. They trace its influence through the motion of stars, the dynamics of galaxies, and the bending of distant light through gravitational lensing. This unusual transparency also narrows the list of possible particle candidates. Any form of dark matter must somehow remain invisible across the entire electromagnetic spectrum. The universe is telling us that something massive exists, and at the same time telling us that our normal methods of seeing are not enough to reveal it. Dark matter also seems to interact only weakly with ordinary atoms. If invisible matter collided frequently with normal matter, the universe would feel noticeably different. Gas clouds would heat up in unexpected ways. Stars might lose energy faster. Even planets and people moving through space might experience a faint drag as they traveled through a sea of unseen particles. Yet none of these effects are observed. Instead, the evidence suggests that ordinary matter and dark matter mostly pass through each other almost without interaction. That is why experiments searching for dark matter must wait for extremely rare events. Perhaps a single interaction over months or years inside a carefully shielded detector. This weak interaction also explains why dark matter remains distributed in extended halos, rather than collapsing into dense disks like ordinary gas. Gas can cool by radiating energy. Dark matter cannot. Without efficient cooling, it cannot settle into thin, rotating structures. Instead, it forms vast, diffuse halos surrounding galaxies. The emerging picture is almost ghost-like. An enormous population of particles carrying mass and gravity, yet barely participating in the familiar chemistry of the universe. Dark matter appears to be cold, meaning it moves relatively slowly. The word cold in cosmology does not refer to temperature in the usual sense. Instead, it describes how quickly the particles move. If dark matter particles moved extremely fast, close to the speed of light, they would smear out small structures as the universe evolved. Rapid motion would smooth away tiny clumps of matter before gravity had time to gather them. But the universe we observe contains abundant small structures: dwarf galaxies, satellite systems, and compact halos. This suggests that dark matter particles had relatively low random speeds early in cosmic history. Such cold particles can remain inside small gravitational wells. These wells then merge over time, building progressively larger structures. In simulations, cold dark matter produces a rich hierarchy of halos and subhalos across many scales. Many of these small substructures may still orbit inside the larger halos of galaxies today. Warm dark matter would produce a smoother universe. If dark matter particles moved somewhat faster in the early universe, they would escape from the smallest density peaks before gravity could trap them. This would erase the tiniest structures. The result would be fewer small halos and fewer early building blocks for galaxy formation. The pattern of galaxies on the smallest scales would look noticeably different. Some scientists have explored this possibility because it might help resolve certain small-scale puzzles in galaxy formation. However, any warm dark matter model must still match the detailed structure we observe in intergalactic gas and the abundance of faint galaxies. Astronomers test these ideas by studying delicate cosmic tracers, features that preserve information about small-scale structure across enormous distances. If dark matter is too warm, the universe becomes too smooth in places where observations clearly show complexity. In this way, the speed of dark matter particles becomes measurable indirectly, simply by examining how structures formed across cosmic history. Fuzzy dark matter introduces an entirely different possibility. Some theories propose that dark matter might behave less like individual particles and more like a quantum wave with an extremely long wavelength. In such models, dark matter would act as an ultralight field extending across entire galaxies. Instead of forming countless tiny clumps, it would produce interference patterns similar to waves overlapping in water. This wave behavior could create a kind of quantum pressure that prevents matter from piling up too sharply at the centers of halos. The result would be smoother central regions in galaxies. Testing this idea requires precise observations of galaxy cores, where the details of the mass distribution are especially important. If correct, fuzzy dark matter would connect the largest cosmic structures with the strange laws of quantum mechanics. Self-interacting dark matter could reshape galaxy centers. Another possibility is that dark matter particles interact with each other, but only weakly with ordinary matter. Even small amounts of self-interaction could slowly redistribute energy within halos over billions of years. In dense regions, collisions between dark matter particles could move energy outward, softening the central concentration of mass. This might help explain why some galaxies appear to have smoother central density profiles than predicted by simple cold dark matter models. However, such interactions cannot be too strong. Observations of galaxy clusters suggest that dark matter passes through collisions with very little drag. That places strict limits on how frequently particles can interact with each other. The viable possibilities lie within a narrow and fascinating range. Too little interaction changes nothing. Too much interaction contradicts observations. Some galaxies appear to contain surprisingly little dark matter. A few faint galaxies have puzzled astronomers by behaving as if they contain far less dark matter than expected. These galaxies remain gravitationally bound, and their stars move in stable orbits. Yet the usual excess gravitational pull appears to be weak. One well-known example involves a galaxy identified using the Dragonfly telephoto array, called NGC 1052-DF2. Initial measurements suggested that the stars inside it move more slowly than expected if a massive dark halo were present. This sparked intense debate. Even small uncertainties in distance measurements can dramatically change the inferred mass of a galaxy. Another possibility is that interactions with nearby galaxies stripped away some of the dark matter. If galaxies truly exist without significant dark matter, they would challenge the idea that every galaxy forms inside a massive halo. They would become rare and fascinating exceptions that sharpen our understanding of cosmic structure. Other galaxies are dominated almost entirely by dark matter. At the opposite extreme, some galaxies contain very few stars compared to their enormous size. These are known as ultra-diffuse galaxies. They can be as large as the Milky Way while containing only a tiny fraction of its stars. In certain cases, the motion of their stars suggests that an enormous invisible halo provides most of the gravitational pull. One candidate, known as Dragonfly 44, may contain an unusually high amount of dark matter relative to its starlight. These ghost-like systems show that galaxies can exist where visible matter is only a minor component. Understanding how such galaxies form may reveal new clues about how dark matter shapes cosmic evolution. Dwarf galaxies act as laboratories for studying dark matter. Small dwarf galaxies contain relatively little ordinary matter. Because of this, the influence of dark matter becomes easier to study. Astronomers measure the motions of stars within these galaxies. If the stars move faster than the visible mass can explain, the extra gravity reveals the presence of dark matter. Some ultra-faint dwarf galaxies contain only a handful of stars, yet remain gravitationally bound. This leads to astonishing mass-to-light ratios, suggesting that invisible matter dominates their structure. Dwarf galaxies also preserve ancient stars formed early in the universe. These stars carry chemical fingerprints of the earliest cosmic environments. As a result, dwarf galaxies offer a unique combination. They reveal both the gravitational structure of dark matter halos and a fossil record of early star formation. Satellite galaxies orbiting the Milky Way allow astronomers to test dark matter on small cosmic scales. Our galaxy is surrounded by a whole collection of smaller companions. Some are relatively bright, like the Large Magellanic Cloud, while others are extremely faint dwarf galaxies discovered only in recent surveys. These satellites travel through the Milky Way's extended dark matter halo. Their motions, shapes, and internal dynamics are shaped by invisible gravitational forces. Some satellites are stretched into elongated forms. Others are slowly being torn apart into long stellar streams. By measuring how stars move inside these dwarf galaxies, astronomers can determine how strongly they are bound by gravity. Those measurements provide clues about how much dark matter they contain. Small scales like these are especially important because different dark matter models begin to diverge here. If dark matter halos contain many tiny clumps, satellites should experience frequent gravitational disturbances. If the invisible matter is smoother, their evolution would look different. New measurements of satellite motions allow astronomers to reconstruct their past orbits around the Milky Way. By tracing where these galaxies have traveled, scientists can estimate how much material they may have lost through tidal interactions. Each satellite galaxy becomes like a test particle moving through an invisible gravitational field. The missing satellites problem asks why we see fewer dwarf galaxies than some models predict. Computer simulations of cold dark matter often produce large numbers of small subhalos around galaxies like the Milky Way. For many years, astronomers could not find nearly that many dwarf galaxies. This discrepancy became known as the missing satellites problem. It raised an important question. Are the simulations incorrect, or are most small halos simply too dark to detect? One explanation is that many small halos never formed stars. Processes such as cosmic reionization and stellar winds can heat or remove gas from tiny halos. Without gas, star formation cannot occur, leaving the halos essentially invisible. Another explanation is that astronomers simply had not discovered all the dwarf galaxies yet. Ultra-faint dwarfs are extremely difficult to detect. Modern surveys have gradually begun discovering more of them, suggesting that earlier counts were incomplete. The puzzle remains an active area of research, with every new discovery refining our understanding of small-scale structure. The too big to fail problem challenges predictions about dense dwarf galaxies. Even when simulations produce the correct number of small halos, another tension appears. Some simulated halos are massive enough that they should almost certainly have formed visible galaxies. These halos appear too big to fail at forming stars. Yet the brightest dwarf galaxies observed around the Milky Way do not seem to inhabit halos that dense. This discrepancy suggests that either our models of galaxy formation need adjustment, or our understanding of dark matter behavior may be incomplete. Several possible explanations exist. Strong bursts of star formation could redistribute mass within galaxies. Gravitational interactions with the Milky Way might strip away material over time. It is also possible that the Milky Way itself is somewhat unusual compared with the average galaxy. Regardless of the solution, the problem highlights the connection between precise measurements of stellar motions in nearby galaxies and the fundamental nature of dark matter. The core cusp debate asks how mass is distributed at the centers of dark matter halos. Many cold dark matter simulations predict that halos develop extremely dense centers. In these models, the density increases steeply toward the center, a structure known as a cusp. However, observations of some dwarf galaxies and low-surface brightness galaxies suggest that their inner mass distributions may be smoother. Instead of steep cusps, they appear to contain broader cores. This difference matters because the shape of a halo's center carries information about how dark matter behaves. If the discrepancy is real, it might hint at new particle physics, such as self-interactions between dark matter particles. Alternatively, it might reflect the influence of ordinary matter. Gas flows, star formation, and supernova explosions can all alter the gravitational potential within a galaxy. Over time, repeated changes in the central gravitational field could transform a steep cusp into a flatter core. The challenge is that measuring inner mass distributions is difficult. It requires careful modeling of star motions, gas dynamics, and viewing geometry. As a result, the core cusp debate remains an active topic of research. Stellar feedback may reshape dark matter distributions. Stars are not passive inhabitants of galaxies. Massive stars release enormous amounts of radiation, and their deaths as supernovae can push gas outward with tremendous energy. If gas repeatedly flows out from the central regions of a galaxy and later falls back inward, the gravitational potential fluctuates. Dark matter particles respond to these changes. Over many cycles, these particles may migrate to wider orbits, gradually lowering the central density. This process offers a possible explanation for why some galaxies appear to have flatter cores without requiring new physics for dark matter itself. It also makes an interesting prediction. Galaxies that experienced intense bursts of star formation should show stronger reshaping of their inner halos. Very small dwarf galaxies that never formed many stars might retain their original steep density profiles. This connection links stellar evolution and dark matter dynamics into a single cosmic story. Tidal stripping can remove dark matter from orbiting galaxies. When a small galaxy orbits a larger one, it experiences varying gravitational forces across its structure. The side closer to the host galaxy feels a stronger pull than the far side. Over time, this difference can stretch the smaller galaxy and gradually tear material away. Dark matter is often stripped first because it extends farther outward than the stars. As the outer halo is removed, the remaining galaxy may retain its stars for a while, even after losing much of its invisible mass. This process can explain why some satellite galaxies appear elongated or disturbed. It can also produce long streams of stars stretching across the sky. Tidal stripping is not only destructive, it also provides valuable information. By modeling how much mass must be removed to match observations, astronomers can infer the original halo properties of satellite galaxies. Each orbital interaction becomes a slow gravitational experiment conducted over billions of years. Stellar streams can reveal hidden dark matter clumps. When globular clusters or dwarf galaxies are gradually torn apart, Their stars form narrow streams orbiting the Milky Way. These stellar streams are extremely sensitive to gravitational disturbances. If the galaxy's dark matter halo were perfectly smooth, a stellar stream would remain thin and coherent for long periods. But if small dark matter subhalos pass nearby, they can disturb the stream's structure. Such encounters may create gaps, spurs, or broadened regions within the stream. In this way, stellar streams act like cosmic seismographs. They record the gravitational footprints of unseen structures. Modern observatories that map precise stellar positions and motions allow astronomers to study these streams in extraordinary detail. By analyzing their shapes and disruptions, scientists can test whether the Milky Way's halo contains the many small clumps predicted by cold, dark matter models. The galaxy itself becomes the detector, and the streams become the ink tracing invisible structure across the sky. The Gaia mission is mapping stellar motions throughout the Milky Way. Instead of simply photographing stars, the Gaia spacecraft measures their positions and motions with extraordinary precision. It tracks how stars move across the sky and along our line of sight. These measurements create a three-dimensional map of stellar orbits throughout the galaxy. Because those orbits respond to gravity, they reveal the distribution of mass, including invisible mass. By modeling the trajectories of halo stars, globular clusters, and distant satellite galaxies, astronomers can infer the shape and extent of the Milky Way's dark matter halo. Even small deviations in orbital paths can provide important clues. Over time, Gaia's growing dataset allows scientists to separate stars belonging to the galactic disk, the central bulge, and the extended halo. It is another way of weighing the invisible, using only the quiet motion of starlight. Some of the fastest stars in the Milky Way can reveal how heavy our galaxy truly is. A small number of stars move so quickly that they appear almost eager to escape the galaxy entirely. These stars are sometimes accelerated through dramatic gravitational encounters. Close interactions with dense star clusters, or with the supermassive black hole at the center of the Milky Way, can fling them outward at extraordinary speeds. Once launched, these stars travel through the outer regions of the galaxy like natural probes. Their motion contains valuable information. Whether such stars remain bound to the galaxy or eventually escape into intergalactic space depends on the depth of the Milky Way's gravitational well. If the dark matter halo is massive and extended, even extremely fast stars may eventually slow down and fall back toward the galaxy. If the halo is lighter, those same stars may escape forever. Astronomers carefully track these high-velocity stars, measuring both their sideways motion across the sky and their radial motion along the line of sight. Each trajectory becomes a clue about the unseen mass surrounding the galaxy. In a sense, a single runaway star can carry news about the invisible matter that holds the Milky Way together. The escape speed of the Milky Way depends strongly on dark matter. Every gravitational system has a critical speed that separates objects that will remain bound from those that will escape permanently. For Earth, this number is familiar from rocket science. To escape our planet's gravity, a spacecraft must reach roughly 11 kilometers per second. For an entire galaxy, the escape speed is vastly larger and far more difficult to measure. Astronomers estimate this value by studying the fastest stars in the solar neighborhood. By examining the distribution of stellar velocities, they can infer the maximum speed stars can reach while still remaining gravitationally bound. If the escape speed is high, the galaxy must contain more mass spread over a large region. If the escape speed is lower, the halo must be less massive or more compact. This measurement is powerful because it does not require direct observation of the halo itself. It relies only on understanding what speeds are possible within the local gravitational environment. Dark matter may also influence how long stellar streams remain narrow and coherent. When a stellar stream first forms, it can appear as an incredibly thin ribbon stretching across the sky. Over time, gravitational disturbances cause the stream to spread out and become thicker. The rate of this change depends on the gravitational environment through which the stream moves. A smooth halo allows a stream to remain narrow for longer periods. A halo filled with substructures can stir the stream, gradually heating it and making it puffier. This turns the thickness of a stellar stream into a kind of cosmic clock. If a stream remains narrow for billions of years, it suggests that the surrounding gravitational field has been relatively smooth. If it spreads quickly, the halo may contain more internal structure. By reconstructing how stellar streams evolve, astronomers can test different models of dark matter halos. Gaps in stellar streams may reveal encounters with dark matter clumps. When astronomers examine long stellar streams closely, they sometimes find unusual features. Sections may be missing. Narrow gaps may appear along the stream. In some cases, faint spurs of stars extend away from the main structure. One explanation for these features is that a compact clump of dark matter passed nearby. During such an encounter, the gravitational pull from the clump briefly disturbs the stars in the stream. Over time, that disturbance grows into a visible gap or irregularity. Importantly, the clump responsible for the disturbance does not need to contain any stars at all. It may be a purely dark subhalo, a small concentration of invisible matter. Astronomers search for these signatures by mapping stellar streams in exquisite detail and comparing their shapes with computer simulations. When the patterns match, they provide evidence for a population of dark subhalos orbiting inside the Milky Way's halo. It is a little like detecting an unseen fish by observing the ripples it leaves behind in a long line of floating leaves. The Large Magellanic Cloud may be creating a wake in our galaxy's dark halo. The Large Magellanic Cloud is one of the brightest satellite galaxies visible from Earth, but it is not merely a decorative companion in the southern sky. It is a substantial galaxy moving through the outer regions of the Milky Way's halo. As it travels, its gravity pulls on the surrounding dark matter. The halo responds by forming an overdense region trailing behind the cloud, a structure sometimes described as a gravitational wake. That wake then pulls back on the cloud itself. This process is known as dynamical friction. Over time, it gradually slows the motion of the satellite galaxy and alters its orbit. Astronomers search for evidence of this wake by studying the motions of distant halo stars and the trajectories of other satellites that may have been influenced by the disturbance. The phenomenon provides another way of probing the otherwise invisible dark matter halo. Galactic bars can reveal the density of dark matter. Many spiral galaxies contain elongated structures of stars, known as bars, extending across their central regions. These bars rotate slowly within the galaxy's disk. As they rotate, they interact gravitationally with the surrounding dark matter halo. If the halo is very dense near the center, the bar experiences a kind of gravitational drag. Over billions of years, this interaction would cause the bar to slow down. If the halo is less dense, the bar can maintain a faster rotation. Astronomers estimate bar rotation speeds by observing how stars and gas move within barred galaxies. By comparing these measurements with theoretical models, they can infer the density of dark matter near the galactic center. In this way, the rotating bar becomes a probe embedded inside the galaxy's invisible structure. Dark matter also influences the stability of galactic disks. A disk of stars and gas is a delicate balance between gravity, pressure, and rotation. If gravity dominates too strongly, the disk may fragment into large clumps. If rotation and pressure dominate, the disk may remain smooth and form stars only slowly. The dark matter halo contributes additional gravitational support. By shaping the galaxy's overall rotation curve, it helps stabilize the disk, while still allowing smaller regions to collapse and form stars. This influence can determine where spiral arms appear, how easily a galaxy develops a bar, and how stable the disk remains over cosmic time. In this sense, the dark halo is not simply a container for a galaxy. It actively participates in shaping the galaxy's visible structure. Dark matter halos may not be perfectly spherical. It is tempting to imagine a halo as a smooth, round sphere surrounding a galaxy. But gravitational processes rarely produce perfect symmetry. Many theoretical models suggest that dark matter halos are actually triaxial, meaning they have three unequal axes. Instead of a sphere, the halo might resemble a slightly stretched shape, somewhat like an elongated potato. This geometry affects the orbits of stars and satellite galaxies. It also influences how tidal debris spreads when smaller galaxies are torn apart. Astronomers test halo shapes by studying the trajectories of stellar streams and satellite galaxies. One famous example is the Sagittarius stellar stream, which wraps around the Milky Way in a long arc. Its path provides clues about the overall shape of the galaxy's gravitational field. If the halo were perfectly round, the stream would follow a simpler path. If the halo is triaxial, the stream's orbit can shift and twist in characteristic ways. By analyzing these details, astronomers can infer whether the Milky Way's halo is spherical, elongated, or flattened. Some halos may rotate slowly. Dark matter halos may also carry a small amount of angular momentum. Over billions of years, mergers with smaller galaxies and tidal interactions can transfer rotational motion to the halo. If the halo rotates even slightly, it could influence the orbits of stars and satellites. It might shift orbital planes, affect the exchange of angular momentum between galactic bars and halos, and shape how debris spreads after galaxy mergers. Halo rotation may even influence dark matter detection experiments. Because the Earth moves through the halo, the relative motion between our planet and the surrounding dark matter particles affects the speed distribution of particles arriving at detectors. A rotating halo could subtly alter that distribution. Detecting such slow rotation is extremely challenging, but the possibility reminds us that dark matter halos may have complex histories and internal dynamics. The invisible structure of the universe is not static. It has motion, memory, and a long evolutionary story written into its gravitational patterns. Ordinary matter can also be dark, but it cannot explain the full missing mass. When astronomers first encountered the problem of missing mass, they asked a very reasonable question. Perhaps the extra gravity came from ordinary matter that simply did not shine brightly. Cold gas clouds, faint dust, dim stars, and stellar remnants can all hide from easy observation. In principle, a galaxy's halo could contain large numbers of such objects. But ordinary matter always leaves clues. Gas absorbs and emits radiation at specific wavelengths. Dust alters the color of light passing through it. Even extremely faint stars still emit some detectable glow. And even when ordinary matter remains dark, it still interacts with radiation and with other matter. There is also a cosmological limit. The early universe determined the total amount of normal matter through processes such as Big Bang nucleosynthesis, when the first light elements formed, and through precise patterns measured in the cosmic microwave background. These independent measurements agree with each other, and together they show that there simply is not enough ordinary matter to account for the extra gravity observed in galaxies and clusters. So while some darkness in the universe is familiar, the dominant missing mass appears to be something fundamentally different. Hidden planets and faint stars were once considered as possible dark matter candidates. For a time, astronomers wondered whether galactic halos might be filled with enormous numbers of dim objects. These could include wandering planets, brown dwarfs, dead stars, or other compact remnants that emit little light. Such objects are collectively known as massive compact halo objects, or MACHOs. If enough of them existed, they could provide significant gravitational mass without producing much visible light. Fortunately, the universe offers a clever way to test this idea. When a compact object passes in front of a distant star, its gravity briefly magnifies the star's light. The star brightens smoothly for a short time before returning to normal. This phenomenon is known as gravitational microlensing. By monitoring millions of stars over many years, astronomers can count how often such events occur. The result was surprising. While microlensing events do occur, they are far too rare to explain most of the missing mass. Compact objects like faint stars and planets may contribute a small portion of the galaxy's mass, but they cannot account for the dominant dark matter component. Microlensing surveys placed strong limits on compact dark objects. Large observational programs carefully monitored dense star fields in the Magellanic Clouds and toward the center of the Milky Way. These surveys searched for brief, brightening events caused by gravitational microlensing. Each detected event carried information about the mass and motion of the lensing object. Over time, the statistics became clear. If the Milky Way's halo were filled with compact objects of a particular mass range, the sky would produce microlensing events at a predictable rate. But the observed rate was far lower than expected for most plausible mass ranges. This ruled out machos as the primary component of dark matter. Although some compact objects certainly exist in galactic halos, they represent only a small fraction of the required mass. The search for dark matter had to move in a new direction. Neutrinos exist and are dark, but they are too light to build galaxies. Neutrinos are real particles that fill the universe in enormous numbers. Trillions of them pass through your body every second, rarely interacting with anything at all. Because they interact so weakly with matter, neutrinos might seem like perfect candidates for dark matter. However, neutrinos have an important property. They are extremely light. As a result, neutrinos move at very high speeds, especially in the early universe. Fast-moving particles do not easily settle into small gravitational wells. Instead, they stream out of dense regions and spread into emptier areas. A universe dominated by neutrinos would struggle to form small galaxies early in its history. Instead, structures would appear much later and on larger scales. Observations of cosmic structure clearly show that small galaxies formed relatively early. This means neutrinos cannot be the dominant form of dark matter. They contribute some mass to the universe, but not nearly enough to explain the gravitational effects we observe. Many scientists suspect dark matter is a new particle. One of the most exciting possibilities is that dark matter consists of a completely new type of particle, not included in the current standard model of particle physics. Such a particle would need several important properties. It would need mass so that it contributes to gravity. It would need to be stable over billions of years. And it would need to interact very weakly with ordinary matter and radiation. These properties would explain why dark matter collects into halos without forming glowing disks, and why it has remained undetected for so long. Particle physicists have proposed many possible candidates. Among the most famous are WIMPs, or weakly interacting massive particles. WIMPs were once considered leading candidates for dark matter. The appeal of WIMPs was almost poetic. Particles with masses similar to those predicted by certain extensions of the Standard Model could naturally be produced in the early universe in just the right abundance to explain dark matter today. This coincidence was sometimes called the WIMP miracle. For many years, experiments around the world searched for these particles, using underground detectors, space telescopes, and particle accelerators. However, as experiments became more sensitive, the expected signals did not appear. This does not necessarily rule out WIMPs entirely, but it has significantly narrowed the range of possible properties they could have. The absence of detection has pushed researchers to explore more diverse possibilities. Axions represent another promising dark matter candidate. Axions were originally proposed to solve a subtle puzzle in the physics of the strong nuclear force. In solving that problem, theorists discovered that a new particle might naturally arise. Axions would be extremely light, stable, and very difficult to detect, all properties consistent with dark matter. Unlike heavier particles that might collide with atomic nuclei, axions are often searched for as a background field filling space. Under the right conditions, axions could convert into tiny amounts of microwave radiation inside strong magnetic fields. Experiments searching for axions use resonant cavities tuned like radios. They listen carefully for faint signals that could reveal the presence of a cosmic sea of axions surrounding us. Discovering axions would solve two major puzzles at once: the strong force symmetry problem and the mystery of dark matter. Sterile neutrinos represent another intriguing possibility. Sterile neutrinos would be related to the neutrinos we already know, but would interact even more weakly. Unlike ordinary neutrinos, they would not feel the weak nuclear force directly. They might only interact through gravity and through subtle mixing with known neutrino types. If sterile neutrinos exist, with the right mass and lifetime, they could contribute to the universe's dark matter. Astronomers search for indirect hints of these particles by looking for faint X-ray signals that might arise if sterile neutrinos decay very slowly over cosmic time. The evidence so far remains uncertain, but the possibility sits at an interesting crossroads between particle physics, cosmology, and astrophysics. Another possibility is that dark matter might consist of primordial black holes. When we think of black holes, we usually imagine the collapsed remnants of massive stars. But in principle, black holes could also have formed much earlier, long before the first stars ever existed. In the extremely dense conditions shortly after the Big Bang, regions of space that were slightly denser than their surroundings might have collapsed under their own gravity. These collapses could have produced black holes directly from the primordial universe. If enough of these primordial black holes formed within a particular range of masses, they could potentially account for a portion of the missing mass in the cosmos. This idea is appealing because it does not require new particles. Instead, it relies on an extreme but known prediction of general relativity. However, the hypothesis is tightly constrained by many observations. Too many black holes in certain mass ranges would disrupt stellar systems, alter the cosmic microwave background, or produce gravitational lensing effects that astronomers would already have observed. Still, there remain narrow windows of mass where primordial black holes could exist without contradicting observations. The idea remains under active investigation. It also carries a fascinating implication. If dark matter were composed of primordial black holes, the mystery would become a question about the earliest density fluctuations in the infant universe. Any candidate for dark matter must satisfy many different constraints at once. Dark matter is not a single puzzle piece. It is an entire network of clues that must all agree with each other. Any viable explanation must reproduce the pattern of cosmic structure seen across the sky. It must match the growth of galaxies and clusters over billions of years. It must also be consistent with the cosmic microwave background, which records the conditions of the early universe with extraordinary precision. In addition, dark matter candidates must satisfy limits set by direct detection experiments, indirect astrophysical searches, and high-energy particle collider experiments. Each of these methods probes different kinds of interactions. A correct explanation cannot work in only one area. It must thread a narrow path through all of them simultaneously. That is what makes the mystery so difficult and so exciting. When a solution eventually appears that fits every scale, from the smallest particles to the largest cosmic structures, it will represent a profound step forward in our understanding of reality. Direct detection experiments search for tiny collisions with atomic nuclei. One of the most straightforward ideas is to catch a dark matter particle interacting with ordinary matter. In a direct detection experiment, a dark matter particle passing through a detector might collide with an atomic nucleus. The collision would deliver a tiny amount of energy, a minute recoil. The energy involved is incredibly small. In everyday environments, such tiny signals would be completely lost in background noise. To overcome this challenge, scientists built detectors designed to be extremely quiet. They look for a specific signature, a short burst of energy corresponding to a nuclear recoil. Different dark matter particle masses would produce different recoil energies. By studying the distribution of these signals, scientists hope to identify patterns that match theoretical predictions. The main difficulty is that many ordinary processes can mimic these signals. Natural radioactivity, cosmic particles, and environmental noise can all produce similar events. That is why experiments rely on multiple detection methods and strict background controls. If consistent signals appeared across different detectors and materials, it would represent the first non-gravitational evidence of dark matter. Underground laboratories provide a shield from cosmic radiation. At the surface of the Earth, cosmic rays constantly bombard the atmosphere and produce showers of secondary particles. These particles can penetrate buildings and detectors, creating noise that overwhelms rare signals. For dark matter experiments, this noise is unacceptable. The solution is to build detectors deep underground. Mines, mountain tunnels, and underground laboratories provide thick layers of rock that act as natural shielding. Even underground, researchers add additional protection. Detectors are surrounded by water tanks, lead shields, copper layers, and active monitoring systems designed to detect unwanted particles. Materials used in the detectors are carefully selected for extremely low natural radioactivity. Components are cleaned with extraordinary care to remove microscopic contamination. The goal is not only to reduce noise, but also to understand every remaining background source. When something unusual appears in the data, scientists must be confident that it cannot be explained by ordinary processes. Liquid xenon detectors are among the most powerful tools in dark matter searches. Liquid xenon has become one of the most successful materials for direct detection experiments. When energy is deposited inside liquid xenon, it produces two measurable signals. First, it creates a brief flash of ultraviolet light. Second, it liberates electrons that drift upward under the influence of an electric field. When these electrons reach a thin layer of xenon gas above the liquid, they produce a second flash of light. The time delay between the two flashes reveals how deep inside the detector the interaction occurred. The pattern of light across the sensors reveals the horizontal position. Together, these measurements allow scientists to determine the three-dimensional location of every event. Background events tend to occur near the edges of the detector, while the quietest region lies deep in the center. This makes it possible to reject many false signals. Another advantage of xenon detectors is their scalability. Large volumes of xenon can be used while maintaining chemical stability and strong self-shielding properties. As detectors grow larger and quieter, their sensitivity continues to improve. Some experiments search for annual modulation signals. The Earth is not stationary. Our planet orbits the Sun, and the Sun itself moves through the Milky Way. If dark matter forms a halo around our galaxy, the motion of the solar system through that halo could create a kind of dark matter wind. During part of the year, Earth's orbital motion adds to the Sun's motion through the halo. During the opposite part of the year, it partially subtracts from it. This could produce a small seasonal variation in the rate of dark matter interactions. In other words, detectors might record slightly more events during certain months and slightly fewer during others. This phenomenon is known as annual modulation. The challenge is that environmental factors can also vary seasonally. Temperature changes, detector stability, and background radiation must all be carefully monitored. To identify a genuine dark matter modulation signal, experiments must collect data over many years, while maintaining extremely stable operating conditions. The Dharma experiment has reported such a modulation signal. For many years, the Dharma/Libra experiment in Italy has reported observing an annual modulation in its data. The claim is not that individual dark matter events have been identified with certainty. Instead, the overall rate of low-energy events appears to rise and fall in a yearly pattern. The timing of this variation matches what would be expected from Earth moving through a dark matter halo. However, other experiments using different detector materials have not observed compatible signals. This disagreement has sparked a long scientific debate. Possible explanations include unknown background effects, unusual interaction properties, or differences in detector sensitivity. Regardless of the outcome, the controversy has pushed the field toward more rigorous comparisons between experiments. Cryogenic crystal detectors measure tiny vibrations from particle interactions. Some dark matter experiments operate at temperatures close to absolute zero. In these detectors, a particle collision inside a crystal produces a burst of atomic vibrations known as phonons. These vibrations are essentially sound waves at the microscopic level. Sensitive sensors attached to the crystal measure the resulting temperature changes and vibration patterns. Even extremely small energy deposits can be detected this way. Many cryogenic detectors also measure ionization simultaneously. Combining these signals allows scientists to distinguish nuclear recoils from electron recoils caused by background radiation. Operating such detectors is technically challenging. They must remain extremely cold and free from environmental noise. Yet the technology offers extraordinary sensitivity. A crystal becomes almost like a musical instrument. When struck by a particle, it produces a tiny vibrational note that scientists attempt to hear. Indirect detection experiments search for signals produced when dark matter particles interact with each other. If dark matter particles can occasionally collide or annihilate, those interactions might produce ordinary particles such as gamma rays, neutrinos, or antimatter. These secondary particles could then travel through space and eventually reach Earth. Telescopes designed to detect high-energy radiation scan the sky looking for unusual signals that might reveal these processes. The challenge is that the universe is already full of energetic astrophysical sources. Pulsars, supernova remnants, black holes, and cosmic ray interactions all produce gamma rays and other high-energy particles. To identify a dark matter signal, astronomers search for patterns that match theoretical expectations. For example, a signal might appear strongest in regions where dark matter is predicted to be densest, such as the center of our galaxy. It might also have a specific energy spectrum characteristic of particular particle interactions. So far, no signal has been universally accepted as definitive evidence for dark matter annihilation. But the search continues, with each new observation placing tighter constraints on possible models. Gamma-ray telescopes study the center of the Milky Way for unusual signals. The center of our galaxy is one of the most promising places to search for indirect dark matter signals. This region likely contains one of the highest concentrations of dark matter in the Milky Way. If dark matter particles occasionally annihilate each other, the probability of such interactions would increase in denser environments. Space-based observatories, such as the Fermi Gamma-ray Space Telescope, have studied the galactic center in great detail. Some researchers have reported an excess of gamma rays that could potentially be explained by dark matter annihilation. However, the galactic center is also an extremely complicated environment. Many astrophysical processes occur there, including populations of rapidly spinning neutron stars known as millisecond pulsars. These objects can produce gamma rays with similar characteristics. Distinguishing between these possibilities requires careful analysis and improved observations. The mystery remains open. Dwarf spheroidal galaxies are excellent targets for indirect searches. Small satellite galaxies orbiting the Milky Way often contain large amounts of dark matter relative to their visible stars. These galaxies emit very little high-energy radiation from normal astrophysical processes. That makes them ideal targets for indirect detection experiments. If dark matter annihilation produces gamma rays, dwarf spheroidal galaxies might reveal faint but clean signals. Astronomers have observed many of these galaxies using gamma-ray telescopes. So far, no unambiguous signal has been detected. However, the absence of detection still provides valuable information. Each observation sets limits on how frequently dark matter particles can annihilate and what masses they might have. Over time, these limits help narrow the range of possible particle properties. Cosmic rays may also contain hints of dark matter. High-energy particles constantly stream through space. These cosmic rays include protons, electrons, and atomic nuclei accelerated by astrophysical sources. Among them are also rare particles such as positrons, the antimatter counterparts of electrons. Certain dark matter models predict that annihilations could produce additional positrons. Experiments like the alpha magnetic spectrometer aboard the International Space Station measure the energy spectrum of cosmic ray particles with extraordinary precision. At certain energies, scientists have observed an excess of positrons compared with simple astrophysical expectations. Whether this excess originates from dark matter or from nearby pulsars remains uncertain. As with many dark matter searches, the difficulty lies in distinguishing subtle signals from complex astrophysical backgrounds. Particle accelerators attempt to create dark matter in the laboratory. Instead of waiting for dark matter particles to arrive from space, scientists can attempt to produce them in high-energy collisions. The Large Hadron Collider accelerates protons to enormous energies and then collides them together. These collisions recreate conditions similar to those that existed fractions of a second after the Big Bang. If dark matter particles can be produced in such collisions, they would likely escape the detectors without interacting. However, their absence would leave a detectable signature. Physicists measure the total energy and momentum of all visible particles produced in the collision. If some energy appears to be missing, it may indicate that invisible particles carried it away. This technique is known as missing energy detection. So far, no confirmed dark matter particle has been produced at the collider. But the experiments have significantly constrained many theoretical models. The search continues with ever more sensitive detectors and more sophisticated analyses. Dark matter might interact through entirely unknown forces. One possibility is that dark matter belongs to its own hidden sector of physics. In this scenario, dark matter particles interact strongly with each other through forces that ordinary matter cannot feel. These forces might be carried by new particles analogous to photons or gluons, but confined entirely within the dark sector. Only gravity, and perhaps extremely weak mixing between forces, would allow this hidden sector to influence the visible universe. Such models could produce complex dark matter structures, including dark atoms, dark radiation, or even entire dark chemical processes. Testing these ideas requires creative experimental strategies. Because interactions with ordinary matter are so weak, the clues may appear only in subtle astrophysical phenomena or rare laboratory signals. Dark matter may have played a role in shaping the earliest galaxies. In the early universe, small halos of dark matter formed first. Gas then flowed into these halos, eventually forming the first stars and galaxies. The properties of dark matter influence how quickly this process occurs. If dark matter particles are heavy and slow-moving, small halos can form early and merge to create larger structures. If dark matter is lighter or more energetic, early structures might be suppressed. Astronomers search for the earliest galaxies in deep observations made by powerful telescopes. By measuring how many galaxies existed at different times in cosmic history, scientists can test different dark matter scenarios. Each newly discovered distant galaxy becomes a clue about how structure formed in the young universe. Gravitational waves might also reveal primordial black hole dark matter. The discovery of gravitational waves has opened a new way to observe the cosmos. When two black holes merge, they produce ripples in space-time that travel across the universe. Detectors such as LIGO and Virgo measure these waves as tiny distortions in the length of laser interferometers. Some scientists have proposed that if primordial black holes exist in large numbers, their mergers might contribute to the population of gravitational wave signals we observe. By studying the masses and frequencies of black hole mergers, researchers can test whether some of them might originate from primordial black hole populations. The data collected so far is consistent with black holes formed from massive stars. But the possibility of primordial black holes remains under investigation. The mystery of dark matter connects the very small with the very large. Understanding dark matter requires knowledge from many fields of science. Particle physics explores the fundamental building blocks of matter. Astronomy observes the motion of stars and galaxies. Cosmology studies the evolution of the universe as a whole. Each discipline provides different pieces of the puzzle. When combined, they reveal a consistent picture. The universe contains far more mass than we can see, and that mass shapes cosmic history on every scale. From the smallest dwarf galaxies to the largest cosmic filaments, dark matter leaves its gravitational imprint everywhere. Despite decades of study, dark matter remains one of the greatest mysteries in science. Astronomers can measure its gravitational influence with remarkable precision. They can map its distribution across galaxies and clusters. They can simulate how it shapes the cosmic web, stretching across the observable universe. Yet its true nature remains hidden. It neither shines nor reflects light. It does not form atoms, molecules, or stars. It slips quietly through ordinary matter, leaving only subtle gravitational fingerprints. This combination of certainty and mystery makes dark matter unique. We are confident it exists, but we still do not know what it is. Every new telescope, experiment, and theoretical model adds another piece to the puzzle. Some discoveries narrow the range of possibilities. Others open entirely new directions of thought. Science often advances this way. Progress is not always a straight path toward a single answer. Sometimes it is a gradual clearing of possibilities, where each eliminated idea brings us closer to the truth. The search for dark matter has already transformed our understanding of the universe. It has shown that visible matter, the stars, planets, nebulae, and galaxies we admire in the night sky, represents only a small fraction of the cosmic story. Most of the universe is made of something else, something quiet, something invisible, and yet something powerful enough to shape the structure of everything we see. The mystery also reminds us of how much remains to be discovered. Just a century ago, astronomers did not even know that galaxies existed beyond the Milky Way. The universe itself appeared much smaller and simpler. Today we understand that our galaxy is only one among hundreds of billions. And even that vast population of stars represents only a small, visible component of a much larger cosmic structure. Dark matter forms the scaffolding of the universe. Galaxies gather along its filaments. Clusters form where those filaments intersect. Vast, empty voids stretch between them. This structure has evolved for billions of years, guided by gravity acting on matter we still cannot directly observe. Yet the clues are everywhere. In the motion of stars, in the bending of distant light, in the faint ripples of the cosmic microwave background, in the delicate structure of stellar streams and satellite galaxies. Each clue points toward the same quiet conclusion. The universe is far richer than our eyes alone can reveal. And perhaps that realization carries its own kind of calm wonder. We are living in a time when humanity can glimpse the hidden architecture of the cosmos. With patient observation and careful thought, scientists are slowly tracing the outlines of something vast and invisible. The story of dark matter is not only about what we do not know. It is also about how we learn. It is about curiosity, persistence, and the quiet thrill of uncovering secrets written across billions of light years. And as we continue searching, new instruments will look deeper into space. More sensitive detectors will listen for the faintest interactions. Future observatories may reveal the earliest galaxies or map the cosmic web with even greater precision. One day, perhaps, a single experiment or observation will reveal the true nature of dark matter. When that moment arrives, it will reshape our understanding of the universe. Until then, the mystery remains, vast, silent, and patiently waiting to be understood. For now, you can simply imagine the universe as it truly is. A luminous ocean of stars and galaxies drifting within an enormous invisible framework. A cosmic landscape where gravity quietly sculpts structures across unimaginable distances. And all around us, flowing gently through the Milky Way and through the Earth itself, an unseen sea of particles may be passing silently by. You cannot see them. You cannot feel them. Yet their gravity holds galaxies together and guides the evolution of the cosmos. It is a reminder that the universe is deeper, stranger, and more beautiful than it first appears. And with that thought, the mind can slowly relax. The day fades, the stars remain. And somewhere beyond the quiet glow of the night sky, the hidden matter of the universe continues its silent work, shaping galaxies, bending light, and holding the cosmos together. Rest well. The universe will keep its mysteries safe until morning.